Today I will speak about only two interconnected systems, and they are linear. And I will try to convince you that some new small gain results still can be interesting and actually very important. My co-authors are Atamas and Vitalii Slynko, with whom I collaborate during last 5 or 6 years at the University of Würzburg. The results that I will present you are available here on archive, and they are also submitted to the CDC conference, to the next CDC conference. Okay, so let's begin with with some basics, with some very simple examples. The idea of small gain can be explained on this very simple example. We have a linear interconnected system with two subsystems, and if we drop this interconnection part, then the rest is exponentially stable. And then if you apply some interconnection here, so A and B can be interpreted as interconnection gains or intensity of interconnection, then stability can be destroyed. Yeah, if A and B are large and have the same sign, then stability will be indeed destroyed. And the small gain condition can be reads in this particular case as follows. If the absolute value of this gain, of these two gains, the product of the absolute values is smaller than 1, then you have global asymptotic stability for the trivial solution. Okay. And let us speak a little bit about the small gain condition. You have here certain flexibility in the following sense. If this interconnection gain is of a very big size, so this absolute value is very large, then you can still have stability if you compensate it by taking a very small b. Yeah, so the absolute value of b should be very small, so that the product is smaller than 1. So we have this flexibility that one gain can be large and another one should be small. And another remark about small gain condition, that it is only sufficient condition, it is not necessary. Okay. For nonlinear systems like this, some nonlinear versions exist, and they can be derived by means of vector Lyapunov functions or by means of ISS theory. And for example, if you use ISS gains, which are nonlinear functions, then if the composition of these two gains is a strict contraction, then you have global asymptotic stability. This is again the small gain condition, and again you can say that if one gain is large, then the other one must be small. Okay, so but extensions to other kind of systems like infinite dimensional systems or discrete time or switch systems, hybrid systems, etc. exist, and moreover, not only two interconnected systems can be handled by small gain theory or vector Lyapunov functions, but also larger with arbitrary number of subsystems or even infinite number of subsystems. So it's really a natural question that you should ask me what's new, because all this is well known and many extensions exist. And in fact, something new can be provided for non-atomic systems. And in this talk, I will try to convince you that this extension is non-trivial and really interesting and really an important contribution. In order to explain this, I will start with simple motivating examples. Let us consider two scalar interconnected systems, two scalar differential equations, and for simplicity, I take here the same interaction, the same function f. Okay? Let us take function f given by this graph. So here you have b, which can be large. Actually, b is arbitrary number, and c is, say, arbitrary positive number. And you can analyze this system by some basic considerations. This function f tells you that interaction lasts for some time interval, of the length c, and then it disappears. So then this part is cancelled, and you have just exponential decay of solution. And okay, by these simple considerations, you can conclude that for any b, say any positive b and any positive c, you have here asymptotic stability. Okay, it will be non-uniform with respect to initial times, but still you have it. Okay, and what I'm claiming is that non-kind of existing small gain theorems can verify that this interconnection is asymptotically stable. Another, well, this is a bit artificial, I agree. So more practical example is like this. You know that due to some seasonal changes, if you have two plants, then some interaction may be there for the day and absent for the night. So this F can be active for some times, but can be zero for other times. And this is really natural. And in this case, if you look at this function F, what happens if epsilon goes to zero? It means that interaction is for a very short time. And for the rest, the interaction is just zero. And at least intuitively, it should be clear that if epsilon is small enough, then you know, so A is maybe a big number, but fixed, and then you can make epsilon that small that the duration of interaction is very short, and it will not destroy stability, and the system will be asymptotically stable. Okay, and in fact, this A can be arbitrarily large, but then epsilon should be taken small enough. And again, my claim is that this example cannot be treated by any existing small gain results. And the last example is, for the case of unbounded interconnection gains or interconnection functions. Again, for simplicity, I take the same. It is not important for my examples and for my theory. It is just for simplicity. So take f given by this formula, which is plotted here, the graph, and you see that it is unbounded, but the larger the value of f is, the smaller is the duration of interaction. And so my claim is, again, that existing results cannot cope with this kind of interconnections in order to conclude stability, but our results can. As well, the previous examples can be treated by our results. Okay, so now what exists, what kind of small gain theorems exist for time-dependent systems? And I pick up this particular result. I should say that there is a series of papers of these two authors, or maybe sometimes only one of them, but there are several works, and they have really plenty of results, small gain results for time-dependent systems, even for nonlinear systems. Yeah, so this is a big advantage because today I speak only about linear systems. And I pick one particular result, which is designed for linear systems from this paper. And yeah, so let me explain the small gain result from this paper. We have two systems interconnected, so they may have different dimensions, say Rn, Rk. And these are conditions, H1, H2, H3 are conditions that we need to conclude about asymptotic stability of this interconnection. Let us analyze these conditions. Okay, so now, Iason, if I will say something wrong about your results, you should interrupt me immediately and protest, because I will try to interpret your results. I hope that I will do it correctly. Okay.
No problem so far, Sergey.
So,
no
okay.
problem.
So let's see. H1. Each subsystem, so we have two subsystems. We have here one, mu1, phi1, and here phi2 and mu2. How we can interpret these functions? Yeah. So first, this phi1 is nothing but interconnection gain for the input y to the first subsystem. The first subsystem has y as input and x is state. And this function phi I is time-dependent gain. The gain from from the second system to the first subsystem. And yeah, so this implication can be interpreted as a kind of ISS property for the first subsystem. We have input input y, we have state x, and this is the gain of the input. This number can be interpreted as, so beta 1 is a gain of the initial state. The function mu1 should be interpreted as the dissipation property. If mu1 is large, then, well, the integral should be unbounded anyway, but this function grows in time very fast to infinity, and then you have minus, and e to minus big number means that your solution is decay very fast if this function is large. Or vice versa, if it is small constant, for example, then this still decaying, but slowly. Okay, so again, this is the gain for interconnecting gains are these two functions, phi1, phi2 are interconnection gains. Beta 1, beta 2 are, I would say, gains of the initial state. And mu1, mu2 are dissipation properties, or the strength of dissipation. And yeah, these assumptions basically say that subsystems are something like ISS. Okay, the next assumption, H2, tells us the following. You multiply here the gains. Yeah, these are the gain of the initial state. This is the gain of the interaction. And this is the dissipation. And this condition tells you that the dissipation overcomes the influence of gains for large times. So if you send t to infinity, then, yeah, for example, think that beta 1 and phi1 are constant functions or polynomials. And then mu, say, a positive constant. Then you have decaying exponent times a polynomial function, and this limit is always 0. So these two conditions are normally easy to satisfy. Okay. And you can interpret that the influence of gains or of interaction is overcome by dissipation. And the last is the small gain condition. In fact, so this resembles, this product smaller than 1 resembles exactly what we had previously. Here, this product smaller than 1, or composition smaller than identity. And yeah, so this looks very similar. And the gains, gamma 1, gamma 2, are defined here. And what happens here, again, you have product of different types of gains multiplied by something related to dissipation. And then you define these functions, and the product of these two functions should be smaller than 1 for any time t0. Okay? Let me point here. Yason, do you have any comment? I hope I provide a more or less reasonable interpretation of your conditions.
No, Sergey, I have no comment.
Okay, fine.
Okay.
And let me say something bad about, about the last condition. If we think about our previous examples, look at this graph. So this F is interaction, and this phi1 or phi2 is more or less this function F or this function A12. So it is responsible for interaction. And imagine that this function at one time point has extremely large value, but is 0 for all other values. Or so for a while it can be big, but then it is 0. Because you take here supremum over all times, the gain will be very large, and you will not be able to satisfy this condition. This is my explanation why you cannot apply your small gain condition to this case, or similarly also to this case, or to this case. So what we need to take into account that maybe at some time instance, the interaction is strong. But if this time is very short, or maybe it happens again and again, but still for a short time, then the dissipation should kill this interaction or should kill the bad influence of this interaction. And so we need other types of gains. And this will be the main tool in this results, so that we use different type of gains. Okay, so let me set up the problem and introduce notation. We consider two interconnected systems. If you don't like Hilbert spaces, just think that these spaces are exactly like here. So Rn, Rk, so some finite dimensional spaces. The results are new also in this case. And let by omega I denote the evolution operator of decoupled subsystem. So for each decoupled subsystem has, of course, its evolution operator. And let us introduce these continuous functions which estimate the norm of these evolutions operators forward in time or backward in time. If you think about Hurwitz matrix at this place and finite dimensional case, then this product alpha I and beta I will be something like e to the power s minus t multiplied by some constant in the power and before the exponential function. So it is exponentially decaying, say, let it say like this. Okay, so this alpha I, beta I, or gamma I, delta I, they are responsible for description of decay rates or of dissipation properties of decoupled subsystems. Okay, and then we have these coupling terms. Yeah, there is, I will come back to the coupling terms in a minute. There is another additional technical assumption. I will comment, but you should forget it immediately because it's really technical and we can get rid of this assumption. Each decoupled subsystem should be invariant with respect to some cone. For example, in finite dimensional space with respect to a first ortant. And this interconnection terms should have this property, and altogether means that the coupled system will be invariant with respect to a product of K1 and K2, which are two self-adjoint solid cones in this respective Hilbert space. But again, pay not too much attention. This is really technical. This simplifies a lot, and we can get rid of this technical assumption. So important is this and this. And remember that alpha, beta, gamma, delta are responsible for dissipation rates of decoupled subsystems. Okay, so next we introduce which we call so new gains, we call them integral gains. Let's take a look on these gains. So these are numbers defined by these expressions. So what do we have? We have here alpha, 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 so three different alphas, well, not different, but 3 times alphas, and 3 times betas, so beta is here and 2 times here. The functions omega I are just weight functions which help us to make this integral convergent. They are auxiliary technical functions which in many cases can be chosen by constant 1. So this is only a technical device with no very important meaning. But important is following. We have here the interaction, the norm of the interaction. We multiply it by these functions which are responsible for dissipation. And then we take integrals and again multiply with other functions responsible for dissipation and take the integral and again multiply by this, which comes from dissipation properties. Okay?
Okay, can you tell
Yes.
what is J here? So you have PII. Should it be PIJ or?
No, there is no typo. I have checked this.
But you have
on
normal
this slide.
AKI there, right?
Yeah. Okay, I will comment. So first, on this slide, I is always in the same formula. It is different from J. So if he is I, then this J is not equal to I. So if I is 1, then J is 2. This is the first comment. Second, we have here Ji and here Ij. So a kind of closed loop. And here we do not have it. Here Ji and again Ji. Okay? So we can say that these gains, we have two. I is either 1 or 2. We have two gains, which are a kind of closed loop gains. And we take here convolution of the interaction and dissipation. So this is a kind of dissipation, and this is interaction. And instead of taking supremum, if I come back here, we have this is dissipation, actually, and this is the gain. And here you multiply and take supremum. And instead, here we have a convolution. So even if this number is extremely large for a short time interval, so S and P are times. If it is for only short time large, but otherwise it is, say, 0, this integral will be finite and also small, depending on dissipation properties, which are described by alphas and betas. Okay? Okay. And this is really, this double integral takes into account that large values of dissipation for some short times dissipate. So this interaction, the influence of interaction, dissipate over a long time, because here we integrate to infinity. Okay? Yeah, so again, these two gains for I equals 1 or 2 are responsible for a closed loop interaction, and here's nothing closed. Here you have Ji, here Ji, and here Ji. Yeah, so these are two gains which are only for the input from I to J, from system I to system J. And we have two gains of this kind and two gains of this kind, and we put them together in a matrix. So this matrix pi is defined by these numbers. Okay, so now the main result is based on this matrix, and it reads, okay, before I state it, this is again some technical step. I introduce so-called weight functions, which always exist, so that this integral is finite. So I need that any of this, so both integrals should converge. And for given delta I or alpha I can always find qi so that this integral converge and this integral converge. So this is technical step, and again, this is just notation. And now we come to the main result. The main result is this line. So let's look on this. The result says that if the spectral radius of the matrix composed of integral gains is smaller than 1, then the solution can be estimated by this complicated expression. And maybe I should not go to very details about H phi and q, which are defined here below, but just believe me that this three function, h, phi, and q, can be calculated by means of taking some estimations, norms, these gains, etc. So these are just routine, technical routine. This number ak is also not very important. It is a property of the cone, this invariance cone, which is in most of cases just 1. Okay, so you can forget about this. And so the good news that we have estimate for solutions, and then depending on the properties of h, phi, and q, we will have certain decay properties and stability properties, which are the second part of the same theorem. The second part reads as follows. If these additional functions, we have phi, h, and q, so if for phi and h we have these properties, then the whole system, the interconnected system, is stable. So the trivial solution is stable. If in addition we have either the limit of phi is infinity or this integral is unbounded, then the whole system is globally asymptotically stable, not necessarily uniformly. And if in addition to all previous, we require that supremum of this function is bounded, then it will be globally uniformly asymptotically stable. Okay? Yeah, so this is basically the main result. Later, I will give you a coloredly simplified version, say, of this result. And before this, I explain idea of the proof. The idea is as follows. We look for a Lyapunov function in this form. Actually, for linear systems, it is a kind of very standard expression where, maybe important is to notice that we have this term here, because in many designs of Lyapunov functions, usually you weight these two guys in some linear or nonlinear sense, or scaling, and then you try to find a Lyapunov function for the whole system. And we have this additional term. And these functions, we have three functions, v11, v12, and v22, are defined by these expressions. So what's that? Well, basically, these are quadratic forms. And now we like to design the functions pi ij. I and j is either 1 or 2, so that this function will be positive definite and its derivative with respect to the system will be negative definite, which is standard for Lyapunov functions. Okay, so the question is whether we can find these functions, or in finite dimensional cases, these are time-dependent matrices. Otherwise, these are operators. If we can find them to satisfy these two conditions, v positive definite and v dot negative definite. Let's try to do this. So I begin with negative definite property for the derivative of v. Let us take the time derivative of this function defined by these expressions along solutions of our system. We have here three summands. Each of them is a scalar product of this form. If we take time derivative, then it becomes very long. We have again three summands. So this is the first one. So three scalar products. And if we look at these scalar products, we can require that, for example, let's take the middle term. Let us require that this expression is just equal to 0, what is written here in the last but one line on the slide. So we require that this is just 0, and the middle term will disappear. And then we require that in the first term, this expression is just minus identity times q1. Identity is identity operator or identity matrix. And q1 is a positive function which was defined before we have needed. So this was continuous, strictly positive function, which was needed here to guarantee convergence of some integrals. So these are our requirements, 1, 2, 3. And if these requirements are satisfied, then finally we get the negative definiteness of the time derivative of our Lyapunov function. Okay, so we still have to come back then to the function v, whether it is positive definite and which properties it has, but still let me finish this time derivative. Okay, these are differential equations in order to find P11, P12, and P22. We have 3 unknowns and 3 differential equations, which we can convert to integral equations. Just this is more or less equivalent transformation of these differential equations. And now we have 3 integral equations for 3 unknown operators. The last line tells us that P12 can be calculated already if you know P11 and P22. So if this is found, if you have found these two, then this is calculated immediately. So basically you can substitute this expression P12 at this place. So star means a joint operator. And so you can exclude one unknown from consideration. So finally, we will have 2 unknown operators for which we have 2 integral equations, which will look after substitution terribly. Okay, but still these are integral equations, which can be compactly written in this way, where Qi are some terrible expressions and Fi is again some map, which looks terribly, but we can write it down. And then we can consider these 2 integral equations, or say the right-hand side here, as a mapping from this pair to this pair. And then we can apply a suitable fixed point theorem, which I will do not show you now. But you should believe me that for a suitable fixed point theorem, we will, of course, need some contraction properties. And these contraction properties are exactly satisfied if you say that the spectral radius of this gain matrix is smaller than 1. And then you apply this fixed point theorem, which guarantees existence of the desired solutions. And okay, and then this negative definiteness is done. So if this spectral radius is smaller than 1 of this matrix, then you will resolve this. So solution exists, and then you check back about v dot, and you will get this desired negative definiteness. So what about positive definiteness for the function v? So let me recall that v is this expression, and we need to have it positive definite. And if we're lucky, it will be a cursive function. Let's check what happens. This fixed point theorem, which gives you existence and uniqueness of solutions for these 2 guys, gives you even more. It gives you estimates for solutions. The norms of these guys can be estimated with some heavy expressions, which basically depends on these gains and on the gain matrix. Okay, and after having these estimates, you can also derive estimate for the norm of P12, which is written here. Okay, so you have estimates from above, which allows you to estimate the Lyapunov function from above. After some routine calculations, you will have a strictly positive function multiplied by this norm, to a squared norm. Okay. So we have estimation from above by this function, and using estimates for these quadratic forms, we can derive that this function is even coercive. So v is underbounded by this expression, where function phi is strictly positive. So we have estimate from above and from below by some positive function h and phi multiplied by the squared norm. So we have both decay property for the function v and the estimate estimates for v from below and above, and this allows us to derive the promised estimate for the solutions. From this, you can derive this estimate. And the rest is to check that under some additional properties, you will have stability or asymptotic stability or even uniform asymptotic stability. So this is just routine to check. So this is the sketch of the proof of the theorem, and then the next is the corollary. In the theorem, you need to check spectral properties of matrix P for any t0, but instead you can take the limit when t goes to infinity, and you can check only this for this limit matrix pi that its spectral radius is less than 1. And then after some additional conditions, you will get stability. And after more conditions, you will even get asymptotic stability, which is not uniform, certainly because now t0 is eliminated. You send t0 to infinity, and uniform asymptotic stability you will not get, but you can get asymptotic stability. Well, finally, you may ask me if I have some example to compare existing results to our results, with our results. And indeed, we can take this example from the already mentioned paper of Karafilis and Tsinias. They have demonstrated that for this interconnected linear system, where parameters A1, A2 are arbitrary numbers, and K is this intensity, which is a positive number, intensity of interconnection. K is a dissipation. Large K means that the second subsystem has a strong dissipation. In this paper, they have applied their small gain theorem and derived that under this condition, if A1, A2 are scaling of interaction, and if the absolute value of their product is small enough, so this is square root of e to the power 3 times k divided by 8, then the whole system is asymptotic, well, non-uniformly, but asymptotically stable. This is their result. By the way, it should be mentioned that the interconnection function is unbounded. So here it is with linear growth, but this is compensated by the exponential decay of another interacting function. Okay, yeah, and if we apply our corollary, then it turns out that this condition can be dropped completely. So you do not need any restrictions like this for all real numbers A1, A2, and any positive k, which is of course needed for dissipation. You will have guarantee for asymptotic stability, which is of course non-uniform. And just quick calculations, we can derive a comparison system which will have this Warshawski property. This invariance over cons is called Warshawski conditions or Warshawski properties. So we can easily derive a comparison system by using these Lyapunov functions. And then we check all these dissipation properties, alphas, betas, gamma, etc. We can calculate them explicitly. These omega 1, omega 2 were auxiliary functions in order to help to converge some integrals. Yeah, so here is 1 and here it is a quadratic function. And after that, we can calculate, this is just routine to calculate all the gains. And then in the corollary, we take the limit when t0 goes to infinity. And if we take the limit matrix is like this, and its spectral radius is just 0, which is of course smaller than 1. So the small gain condition is satisfied. And then in the corollary, there are some additional additional requirements in order to have asymptotic stability. You can check also this, and I skip. This can be checked. So we have, by our results, guarantee that this system is always asymptotically stable. Yeah, non-uniformly, but asymptotically stable. And we have no other restrictions, only that k is positive, which is, of course, not possible to avoid. Okay. So this is my last slide, conclusions. So we have present small gain theorem, which can be also applied to infinite dimensional systems, but so far for linear systems. And the important is that our small gain condition or our integral gains can take into account that there may be some dwell times. It means that for some times you have interaction between subsystems, and for other times it disappears or is very small. And this can be also some, you can have also oscillating coupling functions, and we can take into account all this kind of properties. Okay, and also in direction of conservativeness, it can be checked that if the system is autonomous, then our stability conditions will be the same as classical known stability conditions. Okay, and also our result applies even to the case where interaction functions are unbounded, both from both subsystems, and even can have the same sign, because in case of different signs, there are some other approaches, but this is a hard case where the sign is the same. Okay, this is our results and possible extensions, and some of them are already almost done, I would say. That so first, Dashkovskiy conditions can be dropped. This is invariance with respect to certain cones. This can be dropped. This is not a big deal. More challenging is an extension to more than two interconnected systems, but we have ideas how this can be done. Also, in our results today, all operators are bounded operators, but there are some ideas how to extend to the case of unbounded operators in order to deal with partial differential equations, for example. And also to certain classes of nonlinear systems, we are sure that these results can be extended. Okay, that's all, and I'm open for questions.